All right, today we're cracking open the computer scientist's toolbox. We're going to look at how two totally different ways of thinking, two different algorithms, can attack the very same problem and, well, get some pretty different results. So let's get into it.
Every great tool needs a great problem to solve, and we're going to start with a really big one. Imagine you're put in charge of a massive nationwide infrastructure project. So here's the deal. You've got a map of all the major cities, and your job is to connect every single one of them with fiber optic cable. But you have to use the absolute minimum amount of it possible. I mean, if you just start connecting cities at random, you could waste millions of dollars. So where do you even begin? What's the smartest plan? What you're really looking at here is a classic problem in computer science. In what's called graph theory, the cities are known as vertices, and all those potential cable lines between them are called edges. Each edge has a weight, which in our case is just the distance. The goal, the big prize, is to find something called the minimum spanning tree. It's just a fancy way of saying a network that connects every single city, uses the lowest possible total cable length, and has zero wasted redundant loops. Okay, so how do we solve this thing? We can't just stare at the map and hope for the best, right? We need a clear, repeatable method that we know will work. We need to pull the right tool from our toolbox. At its core, an algorithm is really just a recipe. That's it. It's a set of super clear, step-by-step instructions to get something done. Just like a recipe for baking a cake tells you exactly what to do, preheat the oven, mix the flour. An algorithm gives a computer a perfect roadmap to follow to get to the right answer. And this is where it gets really fun. See, there's no one master recipe that solves everything. For most big problems, there are a bunch of different approaches, or as they're called, paradigms. These are basically different philosophies for how you should write the recipe in the first place. Today, we're going to look at two of the biggest ones. So on one side, you have the greedy approach. This strategy is all about living in the moment. It makes the best possible choice right now, without even thinking about the future. And on the other side, you've got divide and conquer. This one's the methodical planner. It takes a huge, scary problem, breaks it down into smaller, bite-sized pieces, solves those, and then puts it all back together. All right, let's zoom in on that greedy approach first. It's fast, it's pretty intuitive, and honestly, sometimes it's absolutely brilliant. The phrase to remember here is locally optimal. A greedy algorithm doesn't have some grand 10-step plan. Nope. At every single decision point, it just picks the path that looks the very best at that exact moment. It's basically making a bet that if you keep making a series of really good short-term choices, you'll end up with a really good long-term solution. A perfect analogy is making change. Let's say you need to give someone 36 cents. You don't sit there and map out all the possible coin combinations. You just act greedily, right? You grab the biggest coin you can. A quarter. Okay, now you need 11 cents. What's next? You grab the biggest one you can, a dime, and then a penny. It's super fast, super simple, and in this case, it works perfectly every time. So how does this greedy idea apply to our cable problem? Well, there's an algorithm called prims that does exactly this. You just pick any city to start. Let's say vertex 1 here. You look at all its possible connections and greedily choose the shortest one. Boom, the edge to vertex 2. Now your little network has both V1 and V2. So you do it again. What's the cheapest cable to an unconnected city from either V1 or V2? You add that one. And you just keep doing that, always grabbing the cheapest next link until every single city is connected to the network. But of course, there's a catch. This whole live-in-the-moment thing can have a really big flaw. A choice that looks fantastic right now might actually block you from finding an even better solution later on. It can be incredibly short-sighted. Imagine you're a mountain climber, and your goal is to find the absolute highest point in this whole mountain range. A greedy approach would be simple. At every step, just walk uphill. If you did that, you'd end up right here, on this peak labeled M. It's a local maximum. And you think you've won, because every direction from there is downhill. But you've completely missed the actual highest peak, M, because one of your early choices sent you up the wrong mountain altogether. So if the greedy approach can lead you up the wrong mountain, what's the alternative? Let's take a look at our second paradigm, the much more methodical approach called divide and conquer. The whole philosophy of divide and conquer is simple, but man, is it powerful. First, you divide the big problem into smaller, identical versions of itself. Second, you conquer those little subproblems, and if they're still too big, you just divide them again and again until they become so tiny you can solve them instantly. Finally, you combine all those little solutions back together to build up the answer for the original huge problem. The classic example is sorting a giant shuffled deck of cards. You wouldn't try to sort the whole thing in your hands at once, would you? Of course not. You'd instinctively divide it into smaller piles, maybe divide those piles again, until you just have a bunch of tiny stacks that are super easy to put in order. Then, all you have to do is merge those already sorted little stacks back together. This exact process, well, that's a really famous and efficient sorting algorithm called merge sort.
So we've got two very different strategies on the table, the quick and dirty, greedy approach, and the methodical divide and conquer. Which tool is the right one for our big cable-laying problem?
So which one is best? Well, and this is what's so fascinating. For our specific cable-laying problem, the short-sighted, greedy approach actually works perfectly. It's been mathematically proven to always find the best solution. Why? Because this kind of problem has a special quality where the best local choice really does lead to the best overall result. An algorithm like Prim's is great for dense networks where cities have tons of connections. Another greedy one, Kruskal's, works better for sparse networks with fewer connections. The biggest takeaway here is this. There is no single best algorithm for everything. The right tool depends completely on the shape of your problem. And picking the right tool isn't just some academic exercise. It's all about efficiency. It's about time. You saw that time complexity thing on the last slide with the O of something? All that is a way to describe how much longer an algorithm takes to run as the problem gets bigger, like adding more and more cities to our network. Choosing the right algorithm can be the difference between a computer solving a problem in a few seconds versus that same computer taking a few years. It's that critical. But let's just zoom out for a second, because these aren't just abstract ideas for programmers. These are fundamental ways of thinking that, honestly, all of us use every single day. The greedy mindset? That's your intuition. It's your gut feeling. It's fast, simple, and perfect for when you just need a good enough solution right now. The divide and conquer mindset? That's your strategic plan. It's for those huge, overwhelming projects that you have to break down into a to-do list just to figure out where to start. So think about it. When you're trying to plan your week, or you're tackling a massive project at work, or you're just staring into the fridge trying to figure out dinner, which approach do you naturally lean on? Are you being greedy, or are you dividing and conquering? The answer might tell you a whole lot about how you solve problems. Thanks for watching.